If dark matter isn't machos, then there's a good chance that it is WIMPs, weakly interacting massive particles. This is just a class of events, so it's not a single event or a single thing. It's a class of candidate that all have this property that they only interact via gravity and possibly the weak forces. That's something that may allow them to be detected. They are massive, and so they are cold dark matter. So you could think, for example, of something which is a weakly interacting particle, like a neutrino. They are not neutrinos. Neutrinos only interact via gravity and the weak force, but they are very low mass, electron volt masses, if that. Low mass, and therefore their velocity is the speed of light. So they are what you would call hot dark matter. Are there any other relativistic particles? So the point of a WIMP is that it's a weakly interacting massive particle, not any weakly interacting particle. And I'm not a particle physicist. I'm an astronomer by training, and I have put a few things in the PDF about how you can actually go about sort of motivating the idea of WIMPs, because the point about WIMPs is that they are particles that are beyond the standard model. And the standard model is very successful, but there are some issues with it. There's huge ranges of energy that are still unexplored experimentally. Right, we've got to the Higgs, 100 and something gigaelectron volts. We haven't got anywhere near quantum gravity scales, which are important early in the universe. So there's still huge ranges of energy that are unexplored in particle physics. And there are also other issues that exist within it. And basically, you can tweak things without breaking the standard model as it stands to allow a range of plausible additional particles, which are particles which exist beyond the standard model. So you can tweak it to produce WIMPs. But of course, the important point to understand is that when you tweak it, you have to create a class of particle that's not just a very rare, odd thing, because this has to be dark matter. You have to make more mass in the universe from these than you do from all the other particles which exist in the standard model. So, it's, by mass, this is a very, very important bit of the universe. And so there are various suggestions, but I won't go into all of them. What I will just talk about perhaps is, the favourite one, and there's reasons that some people would have this as their favourite, some people may not, and that is something called supersymmetry. And supersymmetry says the following. It says that every particle has its own supersymmetric counterpart. And so this is different than just matter plus antimatter. Supersymmetry introduces basically a new quantum number, if you like. And so as well as having matter plus antimatter, you have something else. And the idea of supersymmetry is it allows the interchange of bosons and fermions. And so, these are bosons are integer spin particles. And fermions are half integer spin particles. And so the point here is that, a boson would be a photon, or the Higgs, for example. And you also have, things like fermions, which are electrons. and quarks. These are all fermions. So you can have various things which are the supersymmetric counterparts of the bosons and the fermions. So for example, you can have, and this is where it really gets a little bit silly, you can have this neutrino, and this neutrino is a boson, and it's the counterpart of the neutrino. Alternatively, you could have the neutralino, that's a fermion, and that's the counterpart of gauge bosons, or the bosons for the weak force, basically. It's actually a little bit more complicated than that, but that's a reasonable explanation. And the principle here is that the bosons all have an S in front of them, so neutrinos, quarks, and so on. So if you take your fermion and turn it into a boson, you put an S in front of the name. If you take your boson and turn it into a fermion, you put lino at the end. So you can also have a Higgsino, for example. So that's the principle of supersymmetry. They're naturally created in some mass hierarchy. There must be. You know, supersymmetric partners do not have the same mass as their counterparts, because otherwise we'd have found them. And therefore that mass must be greater than of order 150 GeV, or we'd have seen it in CERN. With the LHC or something like that. So that's, you know, what you can think about for supersymmetry. Most people would say that the most likely supersymmetric counterpart is this thing here called the neutralino, which is why, despite having a slightly complex origin, it's quite important. And the final feature of supersymmetric particles is the following. You know, the supersymmetry quantum number is conserved in multiplication. So if you charge, for example, you conserve charge in addition, right? So if you have some charge on the left-hand side of your equation, you have to have the same charge on your right-hand side of your equation. So supersymmetric particles have your quantum number. So super particles have this quantum number, I'll call it R equals -1, and normal particles have R equals 1. So for example, if I take two neutralinos, I'll just call them with Chi, and I interact those times -1, you conserve it now through multiplication, -1 times -1 equals 1 times 1. So on this side, I have superpartners or supersymmetric particles, and on this side, I have normal stuff. So stuff that has an R of 1. So for example, that might be photons. It might be something else. And we'll come on to looking at that later. Or something like that. But that's important, and that's one of the sort of prime ideas for what your supersymmetric partners might be and how they might lead to dark matter.